We're in the physics book. Okay, so today we're going to finish chapter 5. We're just going to keep honing away at those free body diagrams, sigma fx, sigma fy. You should have read the book. You should have done so much already that you should be able to finish this. It's pretty standard after a while. If something's on an incline, we have to use sine and cosine for our weight, etc. We look if something's horizontal, vertical. If it has a horizontal component, it goes in the sigma fx. Vertical goes in the sigma fy. Now, obviously, these problems are much harder than anything you had at your high school. So the idea isn't that you just, if you think in your head and you don't know it right away, that's it. You should learn to look in your notes, study what you've done, and so you can do it. The idea is to learn to study and learn it on your own as well, which is what you're going to have to do in college. Okay, so first, we're just going to start right out with doing a problem, and I'll go over the homework that you had later. Okay, so first, we've done like almost everything. I think that we didn't do, I think we did 539, right? We did everything up to 5, we did including 539. Did we do 539? What? Okay. Let's do 539. Lincoln, can you please read?
As shown in figure 5.34, block A, a mass of 2.25 kilograms. Rest on the laptop. It is connected by a horizontal cord passing over a light frictionless fluid to a hanging block B, mass of 1.30 kilograms. The coefficient of kinetic friction between block A and the tabletop is 0.450. The blocks are released from rest. Draw one or more free body diagrams to find the speed of each block after they move 3 centimeters and the tension to the cord.
Okay, so start by reading that over silently to yourself, then draw your free body diagrams. Tori is out sick. Does anyone know where Samuel or Violet are? Probably Samuel's late. Okay, so you should have drawn something like this. Standard figure. You have the normal, you have the weight, you have the tension, you have the friction. You should always start with your free body diagram. Okay, then you have your hanging block, which only has the tension and the weight. So we have the block on the table, and then we have the hanging block. These are standard things, and you're going to be doing this in the lab. Once you do your free body diagram, you write your sigma fx and sigma fy for the one on the table, and then you write your sigma fy for the one in the air. Yeah. So for something on a table, we have that same standard, tension minus Fk is equal to Ma, your normal minus the weight is equal to 0, so therefore the normal is equal to the weight. It's the same standard procedure. We isolate our normal force, we plug it in for the Fk. Just remember your Fk is mu times the normal. Just do that over and over again. I went through that summary with you, writing your sigma equations, isolating your normal force, plugging it in for Fk. I've gone through that with you multiple times. To find the speed after they move 3 centimeters, you're going to have to do the accelerations. So you're using your sigma equations to get your accelerations. Once you get the acceleration, then you use your uniform acceleration equations to get the speed. Okay, now, so you want to plug in here your mu times the weight, and then you have two simultaneous equations, your sigma fx and your sigma fy for the other block, and you use those to solve simultaneous equations. You can use substitution or elimination. Remember, the one moving down is m negative a. So then we have this, t minus the weight is m negative a, right? We have these two equations. Same standard thing we do over and over. Now, you're using substitution or elimination. You can change all these signs and add these two equations together, or you can isolate t and plug it into the other one. You have to know how to solve those simultaneous equations. From there, you can solve for a. Add those two equations together. That's elimination. You could have also used substitution. It is.
Yeah, my check was canceled. When I was leaving my house, it broke in. It was just late. That was late.
And that you're late today.
You my mom's number. She'd be the one who most likely to take the experience. I live with both. I was accepting the gig because I was finishing my home.
Okay, so we've changed all our signs and we get this. Then you add, so you add this equation and this equation, and that gets rid of t. Okay, so you add the left side of the equation to the right side of the equation. So then you get this, right? Same standard thing we do. You could have isolated your t. If you don't know how to use elimination, you don't have to. You can just isolate the t and plug it in for t here. Okay, so when we add the equations together, we get this plus this. Okay, and then on the right side, we get this plus this. Now, this is basic algebra you should have learned in algebra class. If you find substitution easier, just isolate your t and plug it in. But you need to know how to solve simultaneous equations.
How do you do that? You add the two together.
You add the left side equation together, so you add this one to this one, right? The t goes away, and then you add the right side of the equation together. You can always add a left side and a right side because they're still going to be equal. Connie, if you find it easier, just isolate your t and plug it in.
So we have fuzzy, so
Everything we did these last 2 days.
but what, are we using this kind of software acceleration?
Yes.
Can we do the masses?
These are two of the maths that you are NBA and MA. So,
Oh,
plugging them into the items from MA, we're isolating that answer.
okay.
The same M. So we have here MA and MB. And then here we have MB and MA. They're not all the same M. So you can't cancel them out. If they were all one M, you could cancel them out.
How we did them all in one, the same group picture.
In physics,
Yes. But how do we get these ones? We added, we started out with this was this other one here, which was we added this is what this is equal to that's the same thing as that too. And the same force. So then we changed all these signs to get rid of this t. So we changed this to we add this equation, this one, we have this G is not G is equal to So now pull out the A, let's do this plus this times A, and we divide that down.
You isolate your A, so you get MA plus MB on the right. And then you divide it down like this. Now, this particular situation is always going to come out like this. Always. Okay, so we have this.
I didn't do it, but I plugged it in first and then.
That's okay. By doing it this way, you can just see how it always comes out. Show me if you get your acceleration.
This should just run, that's good, yeah, that's fine, yeah, that's fine, yeah, it's 0.7.
Mine just got 1.
If you rounded it. Okay? This is what you get. All right, now, we're just using our old uniform acceleration equations to get our speed.
Which equation?
So which equation should we use to get our speed? We know the acceleration. We know the distance. What's the initial velocity? 0. We're looking for the final velocity. What equation should we use? We don't know the time. V squared. Now, they ask you for the tension in V. So you can use either one of the sigma fx or the sigma fy equations you wrote to get your tension.
When you say the uniform, like, what's the word?
What?
Uniform square, you're talking about like V squared.
Final squared equals V initial squared plus 2 times acceleration times the delta x. You know your initial velocity is 0. You're looking for the final. You know the distance. You need to put that in meters.
So you're looking for these three pieces and then you got your acceleration and it's meters. And your acceleration.
You get it. What do you have, Connie?
For tension,
Yeah.
I got 11.7.
Okay, good. So when we plug that into the V square, we get 0.218 meters per second squared. And then you can use either equation to get your tension. Use plug in to get that T. Okay. All right. Now, you should get the idea of the general equation. Plugging in the numbers, the general equation is always the same in this situation. As I said earlier, you could have isolated your T and plugged it into the other one if you want to use substitution instead of elimination. But these equations always come out like this. And it should make sense to you that the tension is the difference between the weight and the acceleration. Now, if it were not accelerating, our tension would be equal to the weight. Okay, now let's do 41. Jessica, can you please read 41?
A large crate with mass M rests on a horizontal floor. The coefficients of friction between the crate and the floor are μs and dk. A woman pushes downward with a force F on the crate at an angle below the horizontal. What magnitude of force F is required to keep the crate moving at constant velocity? If mu s is greater than some critical value, the woman cannot start the crate moving no matter how hard she pushes. Calculate this critical value of mu s.
Okay, so you're drawing your free body diagram. Read it over to yourself and draw the free body diagram. What does that constant velocity tell you?
And then equal to zero.
Right, ma is equal to 0. Now you need to write your sigma Fy and your sigma Fx, and your sigma Fy, the normal force is not simply the weight in the situation. When you have another force acting, your normal force is not simply the weight. So we can draw her force one of two ways. I can draw it coming in like this. She's pushing down.
I thought it was on the angle itself.
You need to distinguish between when the block is on an angle and when the person's pushing on an angle. You can draw it like this, which is the same thing as drawing it like this. They're the same exact thing. No, so write your sigma Fx, your sigma Fy. You can call that pushing force anything. Now that's not tension, right? There's no cord there. There's a force pushing. So we don't call this T. We call the tension T. So we'll just call this F or whatever you want to call it, but don't call it T.
Should be regular 0.
Yeah, because it's constant velocity.
For the FX and F1. Yeah, it would be zero.
Yes. It's not jumping up off the table. So that simplifies things greatly.
That's exactly right. It's equal to 0. It's equal to 0.
You have sign in there.
So
It's not like a block on an incline where we put sign, because the angle's from the vertical, where we put sign in our X for the weight, because the angle's from the vertical. This angle's from the horizontal. So you should have F sigma Fx is going to be F minus F cosine theta minus the force of friction is equal to 0. And sigma Fy, we have the normal force minus the weight minus F sine theta is equal to 0 because that's pointing down. Now, as normal, same old, you isolate your normal force, and then you plug that in for your Fk here, which is mu times the normal. So go through the step-by-step process, right? Sigma Fx, sigma Fy, isolate your Fn, plug the Fn in for your F. And then you're solving simultaneous equations. You have to isolate your F. All you have to do is isolate your F when you're done with everything, so you're not working with numbers, right? The reason we're not working with numbers is they want to show you the equation always comes out like this. So isolate that normal. Plug it in for Fk. Okay, now plug that normal force in for your Fk. So we know F is mu k times the normal. So you're taking your normal and plugging it into your sigma Fx. So that gives you a long equation for your sigma Fx, right? And then you have to isolate your F in that equation. You have two F's in it. So you want to get the F on one side of the equation because you have two F's. Everything else on the other side of the equation, pull out that F. Okay, so we isolated our normal. We plug that in here to our sigma Fx, F cosine theta minus mu k times the normal. You have to distribute this. Distribute this mu k so you can separate out your two terms and put your F on one side of the equation and everything else on the other side of the equation.
So it's a step-by-step thing, something, sigma X, sigma F, sigma Y. And we have mu times the normal, so it's mu times that. It's the same thing we do every time, and we'll push back into our sigma Fx right there, which is mu times the normal, so we have F cosine theta minus G. It's the same thing every time. So we have sigma Fx and sigma Fy. Isolate in these problems with the one dimensional Fk, which is mu times the normal. And Fk is back here, sigma X. So we plug it in, multiply this out, get your two X and one side and everything else on the other.
Once you have that equation for F, that's the equation in every situation, then go on to B. You want to put the F on one side of the equation, pull it out.
When we pull out an F, there's only two F, right? So you pull the F off.
So just look for Y prime and pull it out. So I have F cosine theta minus mu of k mg minus mu k f sine theta is equal to 0. Okay, now I'm going to get my f's together. F cosine theta, just like when we isolate our f prime, f sine theta, put everything else on the other side of the equation, mu k mg. Now I can pull out the f and divide down. After that, you do b. So we can isolate our f. Just as when we isolate y prime, we put everything with y prime on one side, everything else on the other. Pull out your f, you get cosine theta minus mu k sine theta. Then we divide this down, just as when we isolate. Now this is how it's always going to come out in this situation, always. Now, if she had pushed, I don't know, this were a really huge crate, and she somehow was down pushing up, or let's say she's pulling up rather than pushing down. What would change in our equation if she were pulling up rather than pushing down? What would change? Right, your f sine theta would be a positive f sine theta. Okay, so we'd end up with a positive instead of a negative. Now, what happens in B? In B, if mu s is greater than some critical value, the woman cannot start the crate moving no matter how hard she pushes. Calculate this critical value of mu s. What would we do? Do we have the same free body diagram? Yeah, because everything's equal to 0 when it's not moving, right? Just like when it's not accelerating, everything, we have the same sigma equations. Everything's equal to 0, the same free body diagram. What changes? What? What? Right, what changes in friction?
It becomes already moved.
It's just mu s, that's all that changes. We have the same exact free body diagram, the same sigma equations. Everything's equal to 0 still, so now we have mu s instead of mu k, that's it. Okay, let's do a hard one from back here. So I don't think we've done 589, right?
I don't.
All right, let's do 589. Samuel, can you please read 589?
Block A in figure P5.89 has mass 4 kilograms, and block B has mass 12 kilograms. The coefficient of kinetic friction between block B and the horizontal surface is 0.25. A, what is the mass of block C? Block B is moving to the right and speeding up from acceleration of 2 meters per second squared. B, what is the tension in each core when block B has this acceleration?
Okay, so you have 3 blocks. So you have 3 sets of free body diagrams, 3 sets of sigma equations. But this is a 2-dot problem because nothing's on an angle. So do your 3 free body diagrams with 3 sets of sigma equations. Then you're going to be solving simultaneous equations. First step is physics, everything else is algebra.
So that gives the wave block C,
Um,
or the kilogram mass.
they ask you, what is the mass of block C? So that's what we're solving for. And we're going to go through this in a step-by-step manner. So you can't solve that mass right from the beginning. So first solve what you can. So you're going to have all these unknowns.
But on block B, would we have tension on both sides or just
There's tension on both sides,
okay?
and they're not the same tension, right? Because this isn't a pulley.
So one side would be tension A, one side would be tension C.
Yeah, you can call it TA and TB, or you could call it TAB and TBC. Now, once we hit the pulley, these tensions are the same because we're neglecting the inertia in the pulley.
So is there friction acting? Oh yeah, there's
Okay, so you know you've got these 2 different tensions. This tension here is the same as that one there. So you have 3 blocks. So write your sigma Fy for the 2 hanging blocks, your sigma Fx and sigma Fy for block B. So you're going to have 4 sigma equations. 3 sigma Fy and 1 sigma Fx. You have 4 free body diagrams.
How do you tell if it's a negative in there?
If it's moving down, your acceleration is negative. If it's moving up, it's positive. If it's accelerating to the right, that's positive. If it's accelerating to the left, that's negative. Which one's moving down?
A and C.
They can't both be moving down, right? C is moving down, A is moving up. So our free body diagrams look the same here. TBC, TAB. So you're writing sigma Fy, sigma Fy, sigma Fx, sigma Fy. And you're solving it. Just solve whichever one unknown you can solve. You cannot start by solving the weight. If you can solve for any unknown, solve for it. And then move on solving successively for unknowns.
The last one was equal to zero, because there's no constant velocity if you have acceleration. So what that's gonna be?
I should have put friction in that.
How did you, so you have two frictions?
No, there's just one right here. This FK. Right. It's accelerating to the right, so that's positive. So A is moving up, so that's our positive acceleration. So we have TAB minus MAG is equal to MAA. And then on the right, we have TBC minus MCG is equal to MC negative A. And then in the middle, we have TBC minus TAB minus FK is equal to MA, which this is MBA. Okay, these are our three main equations. And then we have the sigma Fy so these are sigma Fy for the hanging blocks, sigma Fya, sigma Fyb, sigma Fxb, oops, this was C. And then we need sigma Fyb. Well, that's our standard one, right? Normal minus the weight is equal to 0. Because that's not accelerating upward. This part is the physics. Right now you're just doing algebra, solving simultaneous equations. Which equation can you solve first? Just start plugging in numbers and looking at which one can be solved. Once you solve one variable, you can go on to the next one. Now you don't want to start with the hardest one, right? You don't want to start with this. And we don't know the mass of C. So which equation should you start with? This one right here, sigma Fy for it. Okay.
This is MA. And that's what we have.
This one.
Because reconciliation, they told us is two. Did you understand this part here? How did you get from your position? There's three objects, right? Two is in the F plot, one is in the FX, and some in the plot. 1, 2, 3, 4. That's exactly what you have. Now put in what message you're talking about. This is that C. This is the way to C. That's an E. That's an A right here. Oh, they're having much of it. No, you don't do that. You don't need to do that. But they're all, each of mass is separate. That's a mass of A.
Start with the equation you can solve. The equation you can solve right from the beginning is this one. If you don't know what you can solve, just start plugging in numbers and seeing which equation has one unknown. Once you solve one, then you can go on to the next. Yes. You give us the acceleration is 2. Show me if you get your tension AB. Once you get that, just move on to see what you can solve next. Now we're going to do the same thing of isolating our normal force for B and plugging that in for Fk. But we haven't gotten to that equation yet. Lincoln, did you get TAB? Connor, did you get it?
I got 71.45. I mean, wait, which one?
This one right here, TAB.
I think I got 47.2.
Yeah, that's right.
Sorry, I think I did the other person.
Okay, so we get 47.2. Now, when we hit the other tension, remember you have to, once we know this, you're going to have to get rid of this Fk, right? And put in mu times the normal. So we have TBC minus TAB, which is 47.2 newtons, minus mu of K times the normal. What's the normal going to be? Right, it's just the weight. If we have no other vertical force acting, it's just the weight. Okay, so now you get TBC. Once you get TBC, then you can get that other mass. Notice we do all this work before we can solve the mass. But that's okay. Just start solving your equations. Huh? They gave us that as 2.
Yeah, it's on the, I didn't see that.
Oh.
Oh.
This is an issue. That there are two different tensions. Tension on the left, you call it today if you want. It's a different tension than the tension on the right. So hopefully we solve this. That's what you guys are doing. Two. So we solve for TA. And for 47.2.
Right here, Connie.
I hit it way too big.
What did you get for the other tension?
It was, I mean, I haven't got it, but it's gonna be like negative, 1,370.
Okay, so let's see what you're plugging in. So we have TBC. If we isolate this in the equation, right, TBC is equal to 47.2 plus mu of K times MBG plus MBA.
I don't know what that means. I think 45 times 12. Yeah, and oh, I see. I didn't get the TBC by itself first. I think that's what I did wrong. The sun is right.
You should get 100.6 newtons.
Keep going. That was 2, still be 8. Equals.
So we solve for this, right? We got initially. Now we move on to the CFX equation. Where you have T minus so T. This one is T. This is TA. So we have two concerns. Yeah, I know. So T minus TA minus friction, that's right. There's no friction, there's no times in the middle. And the only word we just got there, TA is 47.2. So it's minus 2 million. And it's 47.2 minus 1K times 0, which is the rate. So TV is this. One thing that there is TV is equal to 47.2 plus 1,000 comes out to 100. Okay. Now we go on and we can solve A. So then we use our last equation. Our last sigma Fy of TBC minus MCG is equal to MCA. We're solving for MC. So I have TBC is equal to G plus A MC. So, oh, this was a negative A, sorry. So it's G minus A.
Now, I have TBC over G minus A is equal to MC. Should be 12.9 kilograms. Okay, so we went successively solving equations. If we had that mass from the beginning, they wouldn't have had to give us A. We could have added together all of our equations and done it that way. You should get the idea of just writing the sigma fx, sigma fy. Let's do another one. Use the last equation.
Those we do.
Mass. We asked us for the mass.
Oh, where is it?
Okay. Let's do 573. 573 looks simpler, right? Now, what's different about this, just looking at that figure, is the force is not parallel to the incline. So if you look at like 574 and 590 and all of these that we've been doing, 589, the force is parallel to the incline. But in 573, it's not. So you have to think about your right triangle trig when you do it. Naomi, could you please read 573?
In 8 kilogram boxes sits on a ramp that is applied 33 degrees above the horizontal. The coefficient of kinetic friction between the box and the surface of the ramp is K equals 0.3. A constant horizontal force F equals 16 is applied to the box, and the box moves downward. If the box is initially at rest, what is its speed 2 seconds after the force is applied?
You did not even.
We're doing 73. Okay, so draw your free body diagram. You only have one free body diagram because you have one block.
So force is flat.
The force is horizontal, but you've tilted your axes. Remember, we've tilted our axes. So once you tilt your axes, that force is not horizontal with respect to your axes. So see if you can write your sigma equation.
Would you use cosine or sine?
Well, you're going to be using both. You have your weight is, right, we've tilted our axes, so you have your weight is an angle from the vertical, and then you have your force. Do you know the angle of that force from the horizontal? What? Yes, if you use your geometry, you can figure out what that angle of the force is from the horizontal. It's got to be 33. So your free body diagram, you have the weight, you have the force, you have friction. Okay, so you're going to have friction going up the ramp. Doing that, you can write your sigma fx and your sigma fy. So remember, we tilt our axes. So you have something like this. But this angle is 33 degrees. And this angle here has to also be 33 degrees if you use your geometry.
So I tried to find my
Your force is in both your sigma fx and your sigma fy. Because we've tilted our axes. So it needs to be in both.
So is there no normal force?
Yeah, there's a normal
Is
force.
there no,
Oh yeah, I can put my normal force. So
Okay, that's okay.
Is there no, is one cosine one sine?
yeah,
Okay.
this angle here is from the horizontal, and this angle here is from the vertical. So you're going to have cosine and sine in your sigma fx and in your sigma fy.
How do we know that they're both
Just using geometry. This angle on the tilted axis, this is 33, this is 33, so this is 33. The force is parallel, so it can only be, because the force is parallel to the ground, can only be of the same difference as this right here. Then you isolate your normal force and your sigma Fy. Plug it in for F and your sigma Fx. So you're going to have your weight. Remember, when something is on an incline, how we do our weight. So for sigma fx, we have F times the cosine of 33, okay, plus, now, okay, so if I stick with my frame of reference and I make this a negative, all right, I'm going to change all my signs later, but I'm going to make this a negative because it's going left. Minus the weight, which is going into the third quadrant. So minus mg sine theta. Remember, when we have something on an incline, for our weight, we have sine in the x. Okay, now, we have the friction going up the incline, and this is equal to MA, which is going down the incline. So that's a negative MA. Now I can change all my signs just to make the math easier, right? I can change all three signs. But you should understand, this is my sigma fx. Then you write your sigma fy, you isolate your normal force, you plug it in here. For sigma fy, we have our normal minus our weight cosine theta. And then that force is going upward. So we're going to have F sine theta is equal to 0. Okay. Now, isolate that normal, plug that in here, do the same thing we always do. Okay, get your normal force. You can just solve for that right away. Solve for your normal force, plug it in. They give you the F. They give you the M, you can get the normal force. Plug it into your sigma fx.
Then you calculate it. Or this, just put it to the cosine.
It times 900 times cosine.
Oh, yeah, that's what it
Make sure your calculator's in degree mode. So you have normal. You're starting with this way. You can just isolate that number, 26. So we have our normal is equal to 8 times 9.8 times the cosine of 33 minus 26 times the sine 33. Connor, did you get the normal for us?
I got 51.5.
Good. We get 51.59 newtons. Now we plug that in to our sigma fx equation. So we have minus f cosine 33, 26 cosine 33, minus m minus 8, 9.8. You could have changed all your signs. Sine 33 plus fk, which is the mu of k, times our normal, which is 51.59. All of that was equal to our negative ma. This is just plugging into our sigma fx. From there,
What is it equal?
ma, negative ma. We're solving for a. Show me if you get your a. So we're just plugging in here. Did you have a positive here?
Oh, well, yeah, this.
I can change all my signs. Right, so I get 26 cosine 33 plus 8 times 9.8. Sine 33 minus mu of k times 51.59 is equal to ma. You might find it easier to just change all your signs. Show me if you have the acceleration. So 26 cosine 33 plus 8 times 9.8 times sine 33. Did you put in your mu k?
Yeah. Okay. I'll put that in.
Times 51.59. And then did you divide by your mass?
I did.
I thought it even smaller.
Yeah, you should get, you didn't check, because it's 6.129 meters per second squared.
Yeah.
I got
26.
6.
Sorry about it. I think I did both of them. Oh, I plugged in the negative for 8 times 9.
Okay, so I just changed all my signs. So it started out negative, 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 but I changed all of my signs. You could have done it that way. You could have done minus this, plus this, divided by minus m. When you divide by the minus, it comes out a positive.
So that's it. I didn't fit the right answer. 26%.
So your FK is 0.3 times 51.59, which is 15.48. So if I write this out one last time, we have 26 times the cosine of 33 plus 8 times 9.8 times the sine of 33.
Where did you put the 9.8?
For mg. And then we had minus mu k times that, which comes out to 15.48. Then you get this and you divide the whole thing by the mass, which is 8. Okay, you should get 6.129. You get it? Did anyone get it besides just 129? Okay. So we're going to do one in equilibrium, and then we're going to do another one, and then we're going to wrap up this chapter. But before then, we'll just go on break.